Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss some examples on Cayley-Hamilton theorem. Consider first example. Verify that the matrix A satisfies its characteristic equation and compute A inverse and A raised to 4, where A is square matrix of order 3 by 3, whose first row is 1 to 1, second row is 0, 1, minus 1, and third row is 3, minus 1, 1. We have to find A inverse and A raised to 4 of this square matrix A. First, in the solution, first write given matrix A. We know that characteristic equation of matrix A is determinant of A minus xi equal to 0. Consider the matrix A minus xi equal to given matrix A minus x into identity matrix I of order 3 by 3. Hence, A minus xi equal to square matrix of order 3 by 3, whose first row is 1 minus x, 2, 1. Second row is 0, 1 minus x, minus 1. Third row is 3, minus 1, 1 minus x. Thus, A minus xi can be obtained by subtracting x from the diagonal elements of given matrix A. Thus, A minus xi we calculated. Now, calculate the determinant of A minus xi. That is, we have to take determinant of above matrix. Hence, determinant of A minus xi equal to determinant of order 3 by 3, whose first row is 1 minus x, 2, 1. Second row is 0, 1 minus x, minus 1. Third row is 3, minus 1, 1 minus x. We have to solve this determinant. Hence, determinant of A minus xi equal to 1 in bracket 1 minus x into second bracket. First bracket is 1 minus x into bracket 1 minus x, bracket complete, minus 1, big bracket is complete, minus 2 into bracket 0 plus 3 plus in bracket 0 minus 3 into bracket 1 minus x, close the big bracket. After simplifying these terms, we get determinant of A minus xi equal to minus x cube plus 3x square plus x minus 9. We know that characteristic equation of given matrix A is determinant of A minus xi equal to 0. Hence, x cube minus 3x square minus x plus 9 equal to 0 is the characteristic equation of given matrix A. Cayley-Hamilton theorem states that this characteristic equation is satisfied by matrix A. That means given square matrix A satisfies this characteristic equation. That means replacing x by A, this equation is satisfied. Hence, we get a cube minus 3a square minus a plus 9i equal to 0. We have to check this. That means we have to check that Cayley-Hamilton theorem satisfies this equation. And to solve this equation, we calculate first a square. A square equal to a into a, which is equal to square matrix of order 3 by 3, whose first row is 4, 3, 0. Second row is minus 3, 2, minus 2. Third row is 6, 4, 5. Again, calculate a cube. A cube equal to a square into a. Hence, a cube equal to, take a square from the above equation. Hence, a cube equal to a square into given matrix A equal to, after simplifying we get the square matrix order 3 by 3 whose first row is 4, 11, 1, minus 9, minus 2, minus 7, third row is 21, 11, 7. Now consider the equation a cube minus 3a square minus a plus 9i, which is equal to, substitute the values of a cube, a square, a from the above equations. Hence, we get, after simplifying this equation, we get square matrix of order 3 by 3, which is null matrix. Thus, a cube minus 3a square minus a plus 9i equal to 0. That means every square matrix A satisfies the equation, its characteristic equation. Now, we have to find the A inverse. So, consider the equation a cube minus 3a square minus a plus 9i equal to 0. Pre-multiplying this equation by A inverse, we get, that means we have to multiply this equation by A inverse. A inverse into bracket a cube minus 3a square minus a plus 9i bracket complete equal to A inverse into 0 from the above equation. Value of the bracket is 0 from the above equation. After simplifying, we get A inverse into a cube minus 3 A inverse into a square minus A inverse into a plus 9A inverse equal to 0. That is a square minus 3a minus I plus 9a inverse equal to 0, which gives 9a inverse equal to I plus 3a minus a square. Hence, 9a inverse equal to, substitute the values of a square a from the above equations, we get 9a inverse equal to square matrix of order 3 by 3 whose first row is 0, 3, 3, second row is 3, 2, minus 1, third row is 3, minus 7, minus 1. Hence, A inverse equal to 1 by 9 into square matrix of order 3 by 3. First row is 0, 3, 3, second row is 3, 2, minus 1, third row is 3, minus 7, minus 1. Thus, we have calculated A inverse from the given matrix A, and in this example, we prove that every square matrix satisfies the given equation, its characteristic equation, and here we have calculated A inverse also. Again, multiplying equation 1 by A. Here we have to calculate A raised to 4. So, we multiply given equation 1 by A. Hence, A into bracket a cube minus 3a square minus a plus 9i bracket complete equal to 0. Hence, a raised to 4 minus 3a cube minus a square plus 9a equal to 0. And finally, we get a raised to 4 equal to 3a cube plus a square minus 9a. Substitute the values of a cube, a square, a from the previous equations. Hence, a raised to 4 equal to 3 into a cube plus a square minus 9 into given matrix A. After simplifying, we get a raised to 4 equal to square matrix of order 3 by 3, whose first row is 7, 18, minus 6, minus 30, minus 13, minus 14, 42, 46, 17. Now we solve the second example. Find the characteristic equation of the matrix A given below, and hence find the matrix represented by the term a raised to 8 minus 5a raised to 7 plus 7a raised to 6 minus 3a raised to 5 plus a raised to 4 minus 5a cube plus 8a square minus 2a plus I, where A equal to square matrix of order 3 by 3, which first row is 2 1 1, second row is 0 1 0, third row is 1 1 2. In this example, we have to show that given matrix A satisfies its characteristic equation. That means we have to prove that determinant of A minus xi equal to 0 first. You can take lambda instead of x also. So, the characteristic equation is determinant of A minus lambda I equal to 0. That means subtract only lambda or x from the given matrix. Here we take letter lambda instead of x. Hence, the characteristic equation is determinant, whose first row is 2 minus lambda 1 1, second row is 0 1 minus lambda 0, third row is 1 1 2 minus lambda. Value of the determinant equal to 0. That means this determinant A minus xi is calculated by subtracting lambda from the diagonal elements only. And determinant of A minus lambda equal to 0 is the characteristic equation of given matrix. After simplifying this determinant, we get lambda cube minus 5 lambda square plus 7 lambda minus 3 equal to 0. This is the characteristic equation of given matrix A. We have to prove that this equation is satisfied by A. That means we have to prove CAYLEY-Hamilton theorem. That is, every square matrix satisfies this characteristic equation. Characteristic equation is lambda cube minus 5 lambda square plus 7 lambda minus 3 equal to 0. We have to prove that this equation is satisfied by matrix A. That means replacing value of lambda by A, this equation is satisfied. We have to prove this term. Now, here from CAYLEY-Hamilton theorem, you can prove this term lambda cube minus 5 lambda square plus 7 lambda minus 3 equal to 0 is satisfied by given matrix A. That means you have to calculate first A square, then A cube, and substitute the values of A cube, A square, A in this equation. Lambda cube minus 5 lambda square plus 7 lambda minus 3 equal to 0. After simplification, we get A cube minus 5A square plus 7A minus 3I equal to 0. We can prove this. Now we have to prove the second result. It is similar to the example you have done in schools. For example, divide 11 by 2. Divide 11 by 2. After division, we get quotient as 5 and remainder as 1. So 11 can be written as 2 into 5 plus 1. Like this, we divide here the given term lambda raised to 8 minus 5 lambda raised to 7 plus 7 lambda raised to 6 minus 3 lambda raised to 5 plus lambda raised to 4 minus 5 lambda raised to 3 plus 8 lambda square minus 2 lambda plus 1 by lambda cube minus 5 lambda square plus 7 lambda minus 3. After dividing this term by lambda cube minus 5 lambda square plus 7 lambda minus 3, we get the quotient lambda raised to 5 plus lambda and remainder as lambda square plus lambda plus 1. Hence, in terms of the matrix A, this means a raised to 8 minus 5 into a raised to 7 plus 7 into a raised to 6 minus 3 into a raised to 5 plus a raised to 4 minus 5 into a cube plus 8a square minus 2a plus I equal to, in first bracket, the term is a cube minus 5a square plus 7a minus 3I, bracket complete, into second bracket is a raised to 5 plus a, bracket complete, plus in bracket a square plus a plus I, bracket complete. But every square matrix satisfies its characteristic equation. Hence, we get a cube minus 5a square plus 7a minus 3I equal to 0. Using this term, we get LHS of above equation equal to a square plus a plus I. Now, calculate a square. A square equal to a into a equal to square matrix of order 3 by 3. First row is 5, 4, 4. Second row is 0, 1, 0. Third row is 4, 4, 5. Hence, LHS equal to a square plus a plus I equal to, substitute value of a square, a from the above equations, and also substitute value of identity matrix of order 3 by 3. After simplification, we get matrix of order 3 by 3 whose first row is 8, 5, 5. Second row is 0, 3, 0. Third row is 5, 5, 8. Thus, the given expression equal to square matrix of order 3 by 3 whose first row is 8, 5, 5. Second row is 0, 3, 0. Third row is 5, 5, 8. Now consider next example. Verify CAYLEY-Hamilton theorem for the matrix A and hence find A inverse, where A equal to square matrix of order 3 by 3 whose first row is 1, 2, minus 2. Second row is minus 1, 3, 0. Third row is 0, minus 2, 1. Here we have to show that given matrix A satisfies characteristic equation. Characteristic equation of given matrix A is determinant of A minus xi equal to 0 or determinant A minus lambda I equal to 0. That means subtract only x or lambda from the given matrix and take the determinant. So that characteristic equation is determinant of A minus xi equal to 0 or A minus lambda equal to 0. We take here symbol lambda. So we subtract lambda from the diagonal elements of the given matrix and taking determinant of that matrix, we get determinant order 3 by 3 whose first row is 1 minus lambda, 2, minus 2. Second row is minus 1, 3 minus lambda, 0. Third row is 0, minus 2, 1 minus lambda. Value of the determinant is 0. That is determinant of A minus lambda equal to 0. This is characteristic equation of given matrix A. After simplifying this determinant, we get lambda cube minus 5 lambda square plus 9 lambda minus 1 equal to 0. CAYLEY-Hamilton theorem states that this equation is satisfied by matrix A. That means every matrix A satisfies its characteristic equation. So, in the above equation, we replace lambda by matrix A. Hence, we get equation A cube minus 5A square plus 9A minus I equal to 0. Denote this equation as 1, which is characteristic equation of given matrix A. Now, to solve this equation 1, we calculate first A square. A square equal to A into A. After simplifying, we get 3 by 3 matrix of order 3 by 3 matrix whose first row is minus 1, 12, minus 4, second row is minus 4, 7, 2. Third row is 2, minus 8, 1. Then calculate A cube. A cube equal to A square into A. Take the terms from the previous equations. Hence, A cube equal to, after simplifying, we get 3 by 3 matrix. Whose first row is minus 13, 42, minus 2. Second row is minus 11, 9, 10. Third row is 10, minus 22, minus 3. Now we simplify this equation. A cube minus 5A square plus 9A minus I. Substituting the above values in this equation, we get null matrix of order 3 by 3, whose value is 0. Thus we get A cube minus 5A square plus 9A minus I equal to 0. That means every square matrix satisfies its characteristic equation. This is proved here. Now multiply the above equation by A inverse. Multiplying above equation by A inverse, we get A square minus 5A plus 9I minus A inverse equal to 0. Hence, A inverse equal to A square minus 5A plus 9I. Taking values of A square and A from the previous terms, we get A inverse equal to, after simplifying, we get matrix 3 by 3, whose first row is 3, 2, 6, second row is 1, 1, 2, third row is 2, 2, 5. This is the value of A inverse. That means A inverse equal to this square matrix of order 3 by 3. Thus, in this example, we prove that given matrix A satisfies its characteristic equation, and also we have find A inverse of given matrix. Thank you.